We start with very innocent looking expression, that something like you take say function which is differentiable is necessarily continuous, right. Now I give you a function which is twice differentiable, then immediately you conclude it is also continuous, because when you say twice differentiable it means first derivative exists, second derivative exists. Now the other one you showed that first derivative exists, then it is continuous, right. So that means you have one added premise here, second derivative also exists. Now if some premises are added, then the earlier conclusion still hold, right. So that is a property which is violated in many logics, but that holds in propositional logic and in mathematics in general. So we start with that, that is called the property of monotonicity for the entailment relation. So we start with our first result, which is called monotonicity. So we start with two sets of propositions B where we would say that sigma is a subset of gamma. So there are more premises now. Let W be a proposition so what we say is that if from sigma follows W, then from gamma also follows W. This is one form of the monotonicity. There is another form which says if sigma is unsatisfiable, then so is gamma. So essentially what we do, we assume that sigma entails W, which means every model of sigma is a model of W. Now we want to show that gamma entails W. So let I be a model of gamma, right. Since gamma includes more propositions possibly, then I is also a model of sigma, right. A model of a set means it should satisfy all the propositions at a time. So all the propositions gamma are satisfied by I, therefore all the propositions sigma are also satisfied by I, that is I is also a model of sigma. So once I is a model of sigma, by assumption sigma entails W, so I is a model of W, and that is it. We wanted to show that. If you start with any interpretation which is a model of gamma, it has to be a model of W, that is what we have shown. Is it clear? Okay. So let us write it. Suppose sigma entails W, let I be a model of gamma, as sigma is a subset of gamma, I is also a model of sigma, okay. Since sigma entails W, I is also a model of W, and the proof is complete. We have started with any model of gamma, we have ended with that is a model of W, therefore gamma entails W. So once you have done that, the second one should be immediate, not as a corollary, but we have used the crucial fact that each model of gamma is also a model of sigma. So if sigma is unsatisfiable, there is no model of sigma, therefore there is no model of gamma, because otherwise if there is a model of gamma, then that would have been a model of sigma, whereas sigma has none. Is that right? So we go to the next property. This is easy. Next one is also easy, which says that when you prove something, say sigma entails W, what you do essentially is assume sigma, assume negation of W, derive a contradiction. So as a proof method you always follow it, proof by contradiction, or whose original term is reductio ad absurdum, reduce it to absurdity, right, that is the name. So how do we formulate it now? says, so should we write the complete expression? So this says sigma entails W if and only if sigma union not W is unsatisfiable. Is that right? So you have to write what sigma and W are. It has also another form which plays with this W or not W. So, we say sigma entails not W if and only if sigma union W is unsatisfiable.
In dual by contradiction, you can assume that sigma union not W is satisfiable. Then there exists some model I which satisfies, some model for sigma union not W. This implies that I is a model of sigma and I is also a model for not W. But if I is a model for sigma, then I has to be a model for W, which means I cannot.
Acceptable. But again, you are using the same thing what you are proving, in some sense. You are proving by contradiction. What you are proving? Proof by contradiction.
Not W is unsatisfied.
You are proving proof by contradiction. By contradiction. It's okay. It's not wrong. Can you avoid that? You want to show if sigma entails W, then sigma union not W is unsatisfiable. Okay. So you are assuming sigma entails W. Now how to show this is unsatisfiable? You take any interpretation I that will evaluate it to 0. It will not be a model of sigma union not W, right? That is what you want to show. Because you are starting with models, you are getting problem. Start with the interpretations, so that it is not a model, right? So now suppose I is one interpretation of sigma union not W. You want to show I is not a model of sigma union not W, right? So now you have information on sigma entails W. So that means if I is a model of sigma, it has to be a model of W, right? So it can't be a model of not W. Therefore it is not a model of sigma union not W. Is that clear? But these are for all interpretations which are models of sigma. There can be some interpretations which are not models of sigma, right? So if that is so, then what happens? Okay, provided sigma is non-empty. If sigma is not so, then it is clear from the beginning, right? W is valid if and only if not W is unsatisfiable, right? If sigma is empty, so you forget the empty case. Is it clear now? Okay. So let us write the proof. 1. Let I be a model of, let I be an interpretation. So if I is a model of sigma, we have now two cases. I either is a model of sigma or it is not a model of sigma. If I is a model of sigma, then as sigma entails W, I is a model of W. That is, I is not a model of not W. Okay. Therefore, I is not a model of sigma union not W. Is Is it clear? That proves 1 in the first case when I is a model of sigma. So, if I is not a model of sigma, then I is not a model of sigma union not W. Because sigma union not W is a superset of sigma. So, it is not a model of sigma union not W. So, in either case you get I is not a model of sigma union not W, therefore, sigma union not W is unsatisfiable. Okay. So, that proves one side of that if and only if statement of 1. There is one more, which we have to start from sigma union not W is unsatisfiable, then prove that sigma entails W. Fine. Okay. So, conversely, suppose sigma union not W is unsatisfiable. We want to show that sigma entails W, right. So, how to show sigma entails W? By definition we have to take a model of sigma, so that is a model of W, right. So, we start with a model of sigma. Our aim is to show that I is a model of W. Okay. Now, what happens? I is a model of sigma, but sigma union not W is unsatisfiable. So, that means I is not a model of sigma union not W. What does it say? I of every proposition in sigma equal to 1, but I of not every proposition in sigma union not W is 1. So, where it is going wrong? At not W. So, that means I of not W is 0. So, this says I is not a model of not W, that is I is a model of W. That proves 1. So, you have the ideas, it is not difficult to see what is going on, but only problem you are facing is writing it correctly. That is why I am writing it again. You have to reproduce, this is the way we have to write, there is no other way. You have to use their meta symbols, you have to use the correct arguments and so on, that is all. They are simple otherwise. Now, what about second one? Do you have to prove it again? Replace W by not W by W in the above proof. You would get it. Okay? So, you just write similar to 1. Fine. Now, if you see reduction ad absurdum and compare that with monotonicity, there are two statements similarly in monotonicity. So, can you see what the second one is telling? It says sigma is unsatisfiable, then gamma is also unsatisfiable. Now, instead of sigma, suppose I take sigma union not W, right. If sigma union not W is unsatisfiable, then gamma union not W is unsatisfiable. Okay. Then I get the first one by reduction ad absurdum. Okay. That is why they are listed under the same monotonicity. To see from this to this is not so quick, because this is for arbitrary sigma, not especially in the form sigma union W or not W, but you can always find out one and put it in the form not W, provided you accept the law of double negation. If nothing is negated, then how to bring it? Well, you can take W is equivalent to naught of naught W. So, it is in the form of naught of some x, right. So, that is why both the things are same really due to reduction adaptation. Okay. We will give another common proof procedure which we use in mathematics, that is it is also simple, but we have to formulate it. Suppose you want to prove one conditional statement, right. Say sigma entails x implies y, right, if x then y, then what do you do? Do you just assume sigma and produce if x then y? What you do is you take sigma, along with that assume also x and prove only y, right. But these two are different things. One says sigma entails x implies y, another says sigma union x entails y. Is that right? These two are same. That is what we are going to prove. Okay. So, that is called the deduction theorem. So, we take a set of propositions which will be our premises, and let us take two other propositions. Then what it says is sigma entails x implies y if and only if sigma union x entails y. So, formulation is correct, then you can prove. How to prove this? So, there are again two parts, it is an if and only if statement. So, let us assume sigma entails x implies y, try to show that sigma union x entails y. Okay. So, suppose sigma entails x implies y, our aim is to show sigma union x entails y, fine. So, that means we have to start with a model of sigma union x and end with showing that it is a model of y. Okay. So, let I be a model of sigma union x, since sigma entails x implies y and I is a model of sigma, I has to be a model of x implies y. I is a model of sigma because it is a model of a bigger set. Okay. I of everything in sigma union x is 1. So, I of everything in sigma is also 1, it is a model of sigma. So, now what you have got? I is a model of x implies y, but I is a model of sigma union x. So, that itself gives I is a model of x, fine. Now, I of x equal to 1, I of x implies y equal to 1. What can be y? It can be 0 anyway. If it is 0, then you would get I is a non model of x implies y, right. So, then I is a model of y, that proves first part. Okay. So, we just have to write it, therefore, sigma union x entails y. Now, for the other part, so here we have to show that sigma entails x implies y, right. This is what we have to show. So, you have to start with the model of sigma. So, let I be a model of sigma. Our aim is to show that I is a model of x implies y. Okay. Now, how do we proceed? there will be two cases now, right, because we have x there already. To use that, we have to consider that case first, then we will see if it is not a model, what to do. Okay. So, now case A, it says that if I is a model of x, then we have I as a model of sigma union x, right. Because of this assumption, sigma union x entails y, I has to a model of y, right. So, I of y equal to 1, if I of y equal to 1, I of x implies y equal to 1, that is what we have seen earlier, right. So, then I is also a model of x implies y. What about second case? If I is not a model of x, then clearly I is a model of x implies y, because I of x equal to 0. So, I of x implies y has to be 1. So, there ends the proof. Right now, let us start using this. Suppose we revisit the example what we did in the last class. So, we want to show P implies R implies Q and P implies R entails P implies Q. Let us say this example. Now, to show this, you can always use the truth table that we have done yesterday. Okay. Now, let us see deduction theorem, how is it useful. So, by deduction theorem, since this is one in the form of x implies y, we can use deduction theorem. So, it is enough to show by deduction theorem that P implies R implies Q, P implies R, bring P to this side and tells Q. Is it okay? Now, imagine what is happening in terms of the truth table. In the truth table, you have 8 rows, right. Now, here you have only 4 rows to show it, because P already has been assigned to 1. You have to consider only those interpretations which are models of the premises. Okay. So, P is assigned to 1, half of the truth table goes, right. Now, itself you can construct the truth table and job is over. Is it clear? It will be easier now, right. So, now let us see, if P is 1, P implies R is 1, R has to be 1, you can argue that way also. So, now again another half of the truth table is gone, only 2 interpretations you have to look, give P 1, R 1, Q 0 or 1. Now, with Q 0, this becomes 0, which is not possible, therefore, Q has to be 1, right. It is easy to see now, clear. Now, suppose you want to use reduction ad absurdum. Now, onwards what will you do? Again you can say it is enough to show by reduction ad absurdum that P implies R implies Q, P implies R, P and not Q is unsatisfiable. Okay. Now, how do you proceed? That again is easy, the same way you can argue. Take any interpretation. Okay. In order that you are trying to make it satisfiable, you will be assigning P to 1, Q to 0, because not Q is 1, and then argue. Okay. P is 1, Q is 0. So, since P is 1, P implies R has to be 1. So, R has to be 1. So, now R is 1, Q is 0, P is 1, this is 0, it is unsatisfiable. Right. So, any interpretation which is a model of all these three cannot be a model of this, that is what you have shown. Therefore, this set is unsatisfiable. It is not a particular interpretation you are taking. Your argument is take any interpretation which is a model of all these three, then it can never satisfy this. Therefore, it is unsatisfiable. Okay. One of your laws says that P or not P is valid, right. This is called the law of excluded middle, either P or not P, nothing is in between. There have been many objections to this law, but that is a separate matter. In propositional logic it holds, that we know, because P can be either 0 or 1. Whenever P is 1, you get 1 interpretation. If P is 0, then not P becomes 1, so R is 1, right. So, this statement or this proposition is always evaluated to 1, therefore, it is valid, right. Now, from the validity of P or not P, I can just write that this is also valid. Independently you can see that this is valid, but I am not going for that. What I am asserting is that from the law of excluded middle I can derive that this is also valid. Okay. So, what does that mean? There is something in my mind, so you have to read it. Well, negation of P implies Q is P and not Q, that is the law of implication. Okay. So, there is another law, that means I am using two laws, one is excluded middle, another is negation of P implies Q is P and not Q. This also you use almost everywhere in proving theorems. Suppose P implies Q does not hold, then what do? Assume P, assume not Q and proceed. So, P implies Q is equivalent to its negation is equivalent to P and not Q. Verified by the truth table. What we are asserting is P implies Q, if you consider its negation is P and not Q, right. So, that means I can write first this as P implies Q or P and not Q is equivalent to P implies Q or negation of P implies Q. This is what I am studying, right. Since these two are equivalent, now what I say, this is same thing, since I have excluded middle, x or not x is valid, this is also valid. What about this argument? You are just substituting P implies Q in place of P and then telling that it is correct. There is another substitution here, P and not Q is equivalent to not of P implies Q. So, this substitution is also allowed, and finally, this is equivalent to top since I have law of excluded middle. So, there are two kinds of substitutions involved here, right. First one is P and not Q is equivalent to not of P implies Q. So, which is our Euclidean principle we have followed in geometry, right. Equals can be substituted for equals, that is what we have done here, right. The other one is different. This one is telling something like if x plus y whole square equal to x square plus y square plus 2xy, then 3 plus 4 whole square equal to 3 square plus 4 square plus 2 into 3 into 4, right. So, this is another kind of substitution. In place of these propositional variables, you can substitute any proposition, right, but this needs justification as you have told. How can we say that? Well, we have to prove two substitution theorems now, that equals can be substituted for equals and then uniform substitution can be used, fine. So, let us look at uniform substitution first. So, this is the problem in logic, whatever you have assumed till now you have to prove now. You have assumed always that substitutions can be made, now you have to show that yes, substitutions can be made by using our definition of interpretations and models. Okay. So, let us introduce a symbol, say x is a proposition, p is a propositional variable, y is another proposition possibly different from x, or it can be same as x also. Now, you say x p replaced by y is the proposition obtained from x by substituting each occurrence of p by y in x. Okay. So, that is why it is called uniform substitution. You can read this symbol as p is uniformly replaced by y in x to get the proposition x p equal to y, right. So, an example is here what we have done. In place of p we have substituted p implies q, right, that is what we have done. Then what the statement should be, this is uniform substitution. It says if x is valid, then x p equal to y is also valid. Fine. Now, how do you prove this? That happens now when you become addicted to two wheelers, you will never try to walk. Okay. So, since you are using the terms, interpretations, models and so on, you are forgetting the truth table. Just look at the truth table for x. X is valid, look at the truth table for x. Now, somewhere there p is occurring, p is having 0 or 1, it is a propositional variable, right. So, now instead of p you have substituted y. So, truth value for y can be 0 or 1, even if it is 1 does not matter always, still it is there in the truth table. So, a portion of the truth table is still there, but everywhere x column it is 1. So, everywhere this also will be 1, right. Is it clear? But if you want to give another syntactic proof, proceed by induction, that is also possible. Okay. And that induction can be done many ways, on the number of occurrences of connectives as usual, or you can say how many p's have been replaced, how many occurrence of p is there in x, that is also okay, fine. But this semantics is clear, so there is nothing to do, fine. So, an example is here what we have done, in place of p we have substituted p implies q, right. So, since p or not p is equivalent to top, p implies q or not of p implies q is equivalent to top, that is how it will be used, fine. Next, let us go to equivalent substitution. So, again we have to introduce a notation for equivalent substitution. So, suppose x is a proposition, Well, we can take some more. See, y and z are also propositions. And say y is equivalent to z. We are concerned with equivalences now. Okay. Now, denote by x where y is substituted equivalently. So, we give a subscript here e for that symbol equal to z. So, this is obtained from x by replacing. Now, we are liberal, we do not say each occurrence as we have done in that uniform substitution, that is uniform, this is not uniform necessarily. So, we say by replacing sum of the occurrences of x by y by z. So, this sum may be nothing, may be all. So, let us call this replaced version of x as x, y equivalence replacement with z. So, y is equivalently replaced by z. A precondition is y should be equivalent to z, otherwise you cannot substitute, you cannot use this notation. Fine. Then what do we get? So, what do you have there? You can write equivalence, you can write validity or entailment, some notation you can give. Okay. So, let us write first entailment. If u entails v, then u y equivalently replaced by z should entail v y equivalently replaced by z. Okay. You may go for the second one. If u is equivalent to v, then u y is equivalently replaced by z should be equivalent to v, where y is replaced equivalently with z. So, as a special case you can get, if u is valid, then u where y is replaced by z is also valid, because v you can take as top is a propositional constant, there if you replace nothing happens, it remains the same, right. So, now again how do we prove? Consider the truth table for u and v also, both at the same time, right, a truth table where u occurs, where v also occurs. Fine. Now, when u entails v is evaluated, you are taking some of the portion of the truth table where you have only models for u. In all such cases you find that they are also models of v, right. Now, in u there might be some y's, okay. So, they have been evaluated to either 1 or 0 something, but since y is equivalent to z, so in place of y if you look at z column, there also 0 or 1 correspondingly, right. So, it does not matter in the truth table whether it is y or z, is the truth values which are important in the truth table, fine, and the truth values of y and z are same, right. So, therefore, the truth value columns for u where y is replaced by z or v will be same as u and v, okay. That is all. So, that justifies this statement, okay. Is that answering your question? So, if p or not p is top, sorry, we come from where this one, p and not q can be replaced by not of p implies q, still they will be equivalent, okay. So, these two theorems really give us some way to use our previous laws, whatever laws we have mentioned and some others are there, they can be used now to prove some more equivalences. Right? We can show some equivalences, some consequences to be valid by using those laws.